சார் யூடியூப் லைவ் கொடுத்துட்டேன் சார்.
10 ஆயிட்டு கொடுத்துடலாம்ப்பா, ஆரம்பிச்சிடலாம்.
ஓகே சார், ஓகே சார். So very good morning to one and all present here on this auspicious day. May I request our Associate Professor of Mathematics, Dr. C. Devamanoharan, to welcome the gathering for the day 2. Please, sir.
Good morning to all. On behalf of the Department of Mathematics, University College, I welcome everyone present today's program of International FDP on recent trends in mathematics and extend the same to the guest, Professor Dr. Marudai, Bharidasan University, Trichy. Dr. Marudai is a multidimensional knowledgeable person. That's why his today's lecture is on multivariate calculus. Thank you, one and all present here. Thank you very much.
Thank you.
Thank you, sir, for your crisp and delightful welcome address. Now I invite our HOD and the coordinator of this International Faculty Development Program, Dr. A. Nagarajan, to give a short intro about our resource person, Dr. M. Marudai. Please, sir.
Dear colleagues and my dear professor, teacher, Dr. M. Marudai, person of and all the participants. I will just give a short introduction about our professor. He completed his postgraduate at St. Joseph College, Trichy, and completed his PhD program at IIT Chennai, and joined as a lecturer in NTT Hindu College, Tirunelveli, Pettai, during 1981 to 82, and later he joined in Bharidasan University, Trichy, and his total teaching experience is 40 years, and his research experience is about 21 years. He produced 12 PhD students, and one student is one student completed his PhD thesis. He published more than 80 papers in national and international level journals. Apart from that, he took classes through employment exchange for competitive examinations during his stay in Tirunelveli, and helped a lot of people for getting through bank and TNPSC examination. I personally know that when I am a student, when he first joined, he took a real analysis class for me, and he gives a lot of inspiration as well as interest in real analysis during his during college time. And also he helped a lot of people, not only in mathematics as well as for competitive examinations freely, as well as also through employment exchange, and he conducted a lot of classes, and he is going to various places to conduct classes for competitive examinations. And he is a very nice person, having more helping tendency, and I am really very proud to be a student of him. To this introduction, I over to. Thank you.
Thank you, sir. For every program, the resource person is the key of its success. So I request today's chief guest, the resource person, Dr. M. Marudai, Honorary Professor, Department of Mathematics, Bharidasan University, to deliver his informative lecture to the participants. Please, sir.
Thank you. Thank you. Thank you. Good morning, friends. At the outset, I express my deep sense of gratitude to everyone responsible for this program, including Professor Nagarajan and Mr. Sukalingam Pillai. Personally, I know to him. I am really interested to talk to friends like you, especially from UC College. So I stayed over there for many times, and my stay was so nice and so comfortable. That's why I am grateful to them. Friends, today I am going to talk on multivariate calculus. Actually, it is the extension of linear algebra as well as functional analysis. Actually, it is the foundation course for functional analysis. In the sense, functional analysis for finite dimensional spaces. In functional analysis, we used to come across bounded linear functions. Here, no need of boundedness. Actually, any linear operator from a finite dimensional space to a finite dimensional space is bounded. Therefore, any linear functional from a finite dimensional space is always bounded. Therefore, this program is a foundation course for functions. Friends, I am going to define the derivative of a function of several variables as a linear operator. For that, I have to justify um, um, by providing a non-trivial example for my definition. Not only that, and also I need some definitions in linear algebra, especially linear transformations, and what are all the characterization available for them, especially for finite dimensional spaces. Friends, first you all know vector spaces. So for a vector space, we need to think one thing. Sorry, two things. One is a field. Another one is a non-empty set. V. V is a non-empty set. F is a field.
Sir,
So,
sorry to disturb you. Are you present anything? S-
yeah,
Sir,
sir, I am going to.
sir, your screen is not visible.
V is a non-empty set. I have two operations. One is a binary operation. That's why plus is a binary operation. Therefore, it is a function from V cross V to, and
Are you
another one
present
is a
anything?
function from F cross V to. So I have two operations. One is a binary operation. Another one is just a function. So V together with two operations is said to be a vector space if V under the binary operation plus is an abelian group, and
Sir,
the
sir, your
multiplication,
screen is not.
scalar multiplication. The dot is called scalar multiplication plus is vector addition. This dot satisfies distributive law. So over addition. So you all know very well about what is vector space. So example is R, Rn together with plus comma dot is a vector space. Let X be a subset of Rn. You all know a subset of a vector space is a vector space, a subspace, if and only if there are only two conditions. One is that addition is closed. Next, the dot is well-defined function. If it is so, then X together with the same binary operation plus comma dot is a subspace of Rn. So friends, in Rn, we have lot of things, especially for analysis, any closed and bounded set is compact. There are many things, but now I'm not going to say anything more about on analysis. But Rn is a finite dimensional vector space. You all know what are the standard basis of Rn, how it behaves, and linearly independent and generates these things. You all know, friends. I want I want all of you to know all this, without which this class may be a little bit difficult. Okay. So now, friends, V comma W are vector spaces over the same field, F. So T is a map from V to W. T is said to be linear if and only if I have two conditions. Is linear if and only if. First one is T of V1 plus V2 equal to T of V1 plus T of V2. And the second one is scalar multiplication. T of alpha V equal to alpha times T of V. For every V1, V2, V are in V and alpha is in F. So, a function that satisfies these two conditions is called a linear transformation. Friends, if W is a one-dimensional space or W is a field, then Ft from B to W is called a linear function. Okay, friends, I am going to write some characterization for a function to be linear. For example, first one is f from R to R is linear if and only if there exists alpha belongs to R such that f of x equal to alpha x. So all linear transformations are given by this definition, f of x equal to alpha x. So this is obvious and one can easily prove, and f of x equal to alpha x implies f is linear is obvious. I will go for another one. If f is linear, I am going to find alpha such that f of x equal to alpha x. F is linear, then singleton 1 is the standard basis of R. Standard basis of R. Therefore, f of 1 belongs to R. Let alpha equal to f of 1. Friends, what is f of x? F of x into 1. Here x is a scalar, 1 is a vector. Therefore, since f is linear, this can be written as x into f of 1. What is f of 1? Alpha, that is x alpha. But multiplication is commutative. Therefore, this can be written as alpha x. Therefore, if f is linear, I can find alpha such that f of x equal to alpha x. This is one characterization for a function to be linear from R to R. The second one is f from Rn to R is linear if and only if exists a unique vector y belongs to Rn such that f of x equal to inner product of x and y. It's also called the dot product. What is inner product? For example, in Rn, so what is standard inner product? If x equal to the n tuple x1, etc., xn, and y equal to the n tuple y1, etc., yn, then x dot y is nothing but summation xi y. So friends, this is the standard inner product. Therefore, any linear transformation is a inner product. Friends, now listen here. This is also trivial. That one can easily prove if f of x equal to x dot y, then f is linear. Go for the converse part. If f from Rn to R is linear, then f of ei belongs to R. What is ei? For every I, what is where E1, etc., En is the standard basis of Rn. Friends, now listen here. Now let yi equal to f of ei for every. Then what is f of x equal to f of the n tuple x1, etc., xn, which can be written as f of summation xi. Here, f is linear, therefore this can be written as this is equal to summation f of xi and xi is a scalar, f is linear, therefore this can be written as xi times f of ei. But we know f of ei equal to yi for every I, therefore summation xi yi. By definition, that is a standard interpreter. And friends, it is trivial that y is unique. So I leave it as an exercise to all to the participants. Okay, let us come to the third part. What is the third part? T from Rn to Rm is linear if and only if there exists an m by n matrix A such that T of x equal to Ax. Friends, so if you use the standard basis of Rn and Rm, you can definitely find A. Friends, for that, I'm not going to prove this one, but anyhow, I want to define what is the matrix of a linear transformation. Suppose, let V be a finite dimensional space. V comma W be finite dimensional vector spaces. Let dimension of V equal to n, dimension of W equal to m. Let V1 comma etc Vn comma W1 comma etc Wm be standard basis of V and W. Then T of Vj belongs to W, that is equal to span of W1 comma etc Wm. Therefore, there exists A 1j comma A2j comma etc Amj in F such that T of Vj equal to summation Aij Wi I equal to 1 to m. Friends, but then I am writing this. Therefore, the coordinates of TVJ with respect to the basis of with respect to the basis, what is this? W1 comma etc Wm equal to what is this? A1j comma etc Amj. Friends, now the matrix of T with respect to the basis is defined by, first write um, the first column is the coordinates of TV1. What is TV1? A11, A21, etc. AM1. Sorry, AM1. Next, what is second column? A21, sorry, A12, A22, etc. AM2. Like that, A1, sorry, A1N, comma, etc. AMN. So this is a matrix of T. So using this definition, one can easily prove T from Rn to Rm is linear if and only if there exists an m by n matrix A such that T of x equal to Ax. Okay, friends. First, now I want to prove some results. Let that is L of Rn comma Rm denote vector space of all linear maps from Rn into Rm, and let L of Rn equal to L of Rn comma Rn. Okay. So friends, first I will I will prove the very first result. If A belongs to L of Rn comma Rm, then A is bounded, and hence A is uniformly continuous. Okay. Friends, before proving this theorem, let us see what is the norm of a function. Let f from R, so let it be, let it t from t from that V to R, no sorry, from Rn to Rm, be linear. How to define norm T? There are many definitions and all the norms are equivalent because we are in a finite dimensional space. So what norm T is defined by a supremum of that of all norm Tx such that norm x less than or equal to 1. So supremum of this set of all norm Tx such that norm x is less than or equal to 1. I take this as the norm of T. And one thing, one can easily, using this definition, one can easily prove norm Tx is always less than or equal to norm T into norm x. Friends, this conclusion is obvious and one can easily find in any book. And one more thing I want to say here, norm Tx is less than or equal to alpha times norm x. There is a question that which one is bigger? That is norm T, norm T and alpha. Friends, one thing is obvious. This is the supremum. Supremum means least upper bound. This is upper bound. Which one is bigger, upper bound or least upper bound? Therefore, norm T is always less than or equal to alpha. Thus, we have if norm Tx less than or equal to alpha into norm x, then norm T is always less than or equal to alpha. Okay. So let us prove our theorem. What is our theorem? If T belongs to, A belongs to L of Rn comma Rm, A is bounded and hence it is uniformly convergent. For that, let x belongs to Rn such that norm x is less than or equal to 1. What is x? X is nothing but n tuple x1, etc., xn, which can be written as summation xi ei, where e1, e2, etc., en is the standard base Rn. Okay. Therefore, for every I, mod xi for every I equal to 1 to n, mod xi is always less than or equal to square root of x1 square plus etc., plus xn square. This is less, that is equal to norm x. But norm x is always less than or equal to 1. Therefore, for every I, thus, for every I, mod xi is less than or equal to 1. Friends, what is norm? Ax. This is equal to norm of A of summation xi ei, and A is linear, therefore this can be written as norm of summation A of xi ei, and xi is a scalar, therefore this can be written as norm of summation xi into aei. Friends, by definition, and this is using the triangular inequality, this can be written as norm less than or equal to summation norm xi aei. Friends, xi is a scalar, therefore this can be written as summation mod xi into norm aei. aei. Friends, mod xi is always less than or equal to 1, therefore this is less than or equal to summation norm aei. So friends, this is finite. I write it as m, which is less than infinity because it is finite. It's a finite sum, therefore I equal to 1 to n, therefore it is bounded. Therefore, I can find a suitable m such that summation aei I equal to 1 to n equal to m. Friends, now everything is obvious. What is norm ax minus ay? This can be written as norm of a of x minus y. We know norm ax is always less than or equal to norm a into. So norm a. Friends, one thing I have forgotten that this is true for all x with norm x less than or equal to 1. Therefore, supremum is always less than or equal to m. Therefore, using this norm a is less than or equal to m. Okay. Norm a into norm x minus y, but norm a is less than or equal to m, therefore this is less than or equal to m times norm x minus y. This is just like a Lipschitz map with the Lipschitz constant m, therefore it is a uniformly continuous map. So what I have proved is a linear transformation from a finite-dimensional vector space to a dimensional vector space is always bounded, and hence it is uniformly continuous. Okay. Normally, for a uniformly continuous functions, there are many results available. What are all they? It maps causes sequence to causes sequence. Only one thing I have mentioned. There are many things. Of this, I say only one thing. What is that? That is important. If a function is uniformly continuous, it maps the causes sequence to causes sequence. If xn is causic, f is uniformly continuous means f of xn is definitely a causic sequence. Okay, friends, let us come to next result. But friends, I am interested only in certain things. But anyhow, I will say some results. If A, comma B in எல்லா foreign or எல்லா foreign, and if A is invertible such that norm B minus A times norm A inverse is less than 1, then B is invertible. Friends, this result shows that set of all invertible linear operators is a open set. And not only that, a map that goes A to A inverse is uniformly continuous. Okay. So let us come to differentiation. So let us go to that f function from open interval a comma b to so for differentiation we need only open intervals or open set. You may know why we are taking not going to elaborate anything more about this. Friends, let x in open interval a comma b. We say f is differentiable at x belongs to open interval a comma b if and only if limit h approaches 0 f of x plus h minus f of x by h exists. If it is exists, that is if and only if limit h approaches 0. If it exists, I say this is equal to f dash of x. If and only if f of x plus h minus f of x minus f dash of x at h equal to 0. Int h, sorry, f dash of x at h equal to 0. Friends, I am concentrating more on this. What do you say about a map that sends h to f dash of x into h? Friends, we know f dash of x is f dash of x belongs to R. Therefore, h goes to a scalar multiple of h. Therefore, this map is linear. Is linear. I write it as A. Let A of h equal to f dash of x at h. Then I rewrite my definition. What is my definition? F from open interval a comma b to R is differentiable if and only if there exists a linear map A belongs to L of R such that limit h approaches 0, f of x plus h minus f of x minus a at h divided by h equal to 0. Here, what is a? F dash of x. So, a function is differentiable if and only if we can find a linear operator a belongs to L of R such that limit h approaches 0, f of x plus minus f of x minus ah divided by h equal to 0. Let us extend this result to more general case. So, what is the actual definition? Actual definition is let E be an open subset of and let f from E to Rn. We say f is differentiable at x belongs to E if and only if there exists a linear transformation A belongs to L of Rn comma Rm such that limit h approaches 0 f of x plus h minus f of x minus f dash of x or a at h divided by ln h equal to 0. Here I write a equal to f dash of x. So, friends, I am going to say something more about this. My first remark is let r of x equal to r of h equal to f of x plus h minus f of x minus a at h. this R of h is called a remainder term, and R of h divided by norm h approaches 0 as h approaches 0. In the sense, R of h approaches 0 much faster than as h approaches 0. Friends, now listen here. Very, very interesting concept. Let A belongs to L of Rn comma R. What is already we have proved that it is continuous, not only continuous, uniformly continuous. Now I am going to prove it is differentiable, and at the derivative at any point is the function itself. How? What is A of x plus h minus AH AX minus AH equal to 0, because A is linear. A of x plus h is AH, A of x plus AH minus AX minus AH equal to, that sense 0. Therefore, dividing by norm h also 0. Therefore, limit h approaches 0, this equal to 0. This gives A dash of x equal to 0. So, the friends, this is very, very interesting, especially for CSAR. This question is asked: if A is linear, its derivative at any point is the function itself. Friends, now I am going to give a suitable example to show this. Let f from R2 to R2 be defined by f of x comma y equal to y comma x. What is this? F of x comma y equal to y comma x. So, what about this? Geometrically, we can say more about this. Please, friends, I leave it as an exercise to all of you. Probably, this may be this f is geometrically symmetry with respect to the line y equal to x. You just check it. Friends, now I am going to, this is linear, trivially it is linear. You know, what is this? This can be written as f1 of x comma y, comma f2 of x comma y, and where f1 comma f2, that is f is identically equal to f1 comma f2. F1 comma f2 are called the components. F is linear if and only if each component is linear, and you can, this f1 of x comma y is just a projection. Similarly, f2 of x comma y equal to x is also a projection. You know projection map, and that is open and continuous map. And f is linear is like this. Now listen here. What is f of x plus h minus f of x minus f of h comma k? What is this? This first one is, sorry, I made a mistake. Friends, what is f of x plus h comma y plus k minus f of x comma y minus f of h comma k? What is this? This is equal to y plus k comma x plus h minus y comma x minus h comma k. Friends, this is equal to y plus h comma x plus k minus y plus k comma x plus h. So this is equal to 0. Therefore, norm of f of x plus h comma y plus k minus f of x comma y minus f of h comma k divided by therefore limit h approach h comma k approaches 0, therefore f dash of x comma y at h comma k equal to f of h comma k. This gives f dash of x comma y is identically equal to e. So if f is linear, its derivative at any point is the function itself. Okay, friends. Now I want to write, I want to say something about partial derivatives. Suppose f is a function from R2 to R, and suppose is differentiable. You assume that f is differentiable. Then you all know limit h approaches 0, f of x plus h comma y minus f of x comma y divided by h exists. So this exists, this is equal to dou f by dou x. Friends, I want to write what is x plus h comma y. This is x comma y plus h comma 0. So this is
ஹலோ
nothing but x plus
பாபுண்ணா, குட்
y,
மார்னிங்ண்ணா. ஜாக்சன்
sorry,
பேசுகிறேன்.
x comma y,
ஆனால் ஒன்றும் இல்லைண்ணா, இந்த ப்ரொமோக்காக நம்ம வெப்சைட்ஸுக்குன்னு சில ஃபோட்டோஸ் எடுத்து வச்சாங்க
x
தெரியுமா?
comma y plus h time
அதோட
he1.
என்டையர் ஃபோட்டோஸ் வேணும்ண்ணே.
So
அவங்க சில செலக்டட் ஃபோட்டோஸ்.
therefore
சொல்லுங்கள்.
dou f by dou x, dou
புரியல.
f by dou x at x comma y is
ஆமாம்,
nothing but limit h approaches 0, f of x
காலேஜுக்கு
comma
தரலண்ணே.
y plus h e1
ஓகே ஓகே
minus
ஓகே.
f
பட் அது
of
ஒரு காப்பி
x
வாங்கி
comma
வைங்க.
y divided
இப்போ
by
எனக்கு கிடைச்சாலும் நான் உங்களுக்கு போட்டு விட்றேன்.
h. Similarly, dou f by dou y
சரி, ரைட்ண்ணே,
at
ரைட்ண்ணே,
x comma
ரைட்ண்ணே.
y
ஓகே
equal to limit h approaches 0, f of x comma y plus h e2, here h e2 minus f of x comma y divided by h. In general, this can be extended for any function from Rn to R. So, if f from Rn to
ஹலோ. ப்ரௌசர்,
R
குட் மார்னிங். நல்லா இருக்கீங்களா?
is differentiable,
ப்ரௌசர் ஒன்றும் இல்லை ப்ரௌசர். நம்ம ப்ரொமோஸ்க்கு
then
வெப்சைட்ஸுக்கு வெப்சைட்
dou f
ரீவாம்ப்
by
பண்ணும்போது
dou
நீங்கள்
x
சில ஃபோட்டோஸ் எடுத்தீங்க
at
தெரியுமா?
x
ஃபோட்டோகிராஃபர்
is
கூப்பிட்டு வந்து
nothing but
அந்த ஃபோட்டோஸ்
limit h
தேவைப்படுது
approaches
ப்ரௌசர்.
0, f of x plus h
பாபு
e1
அண்ணன் இல்லை ப்ரௌசர், கேட்டுட்டேன்.
xj
நீங்கள்
xj
வாட்ஸ்அப்பில் எனக்கு ஃபோட்டோஸ்
h
அனுப்பிச்சிங்கன்னா அந்த
ej minus f of
அதை
x
மட்டும் எனக்கு கொஞ்சம் மெயிலில் அனுப்பிக்க
divided by
முடியுமா
h.
ப்ரௌசர்?
Friends, what is this? h e1 means
இல்லை அதான்
the second derivative.
இல்லை
Partial derivative with
அதான்
respect to
அந்த
second
அந்த
derivative.
ஃபோட்டோஸை அப்படியே எனக்கு மெயில்
h
அனுப்புங்க ப்ரௌசர்.
e1
ஏன்னா
means
வாட்ஸ்அப்பில் அனுப்பும்போது
partial
அதோட
derivative
கிளாரிட்டி
with
கம்மியாகும்.
respect to first
மெயிலில்
derivative.
ஃபைலாக
So
அனுப்பிடுங்க.
I write it as
ஓகே ஓகே ப்ரௌசர், ஓகே ப்ரௌசர்.
now
தேங்க்யூ
I
ப்ரௌசர்.
write it as dj
சரி
f of
ப்ரௌசர்.
x by
ம்
dou
ம்
f
ம்
by dou xj
ஓ
at x.
சரி
This
சரி
is
சரி
just
சரி.
a notation. One can easily prove if f from Rn to
தெரில.
or
ஓ
f from uh,
ஓகே ப்ரௌசர், ஓகே ப்ரௌசர். நீங்கள் இப்போ உங்கள்
Rn
கையில்
to
இருக்க ஃபோட்டோஸ் மட்டும்
Rn
எனக்கு அனுப்புங்க. நான் ஐகாக்கு நான் பின்னி கேட்குறேன் ப்ரௌசர்.
is differentiable,
தேங்க்யூ ப்ரௌசர், தேங்க்யூ ப்ரௌசர்.
then all partial derivatives exist and f dash of x at ej equal to summation dj fi of x duy I equal to 1 to n. Friends, this is just a theorem. One can easily get through this. And what is this? F dash of x at ej, where e1, u2, etc. en is the standard basis of Rn. u1, u2, etc. um is the standard basis of Rm. So, friends, this theorem helps me to write the matrix of a linear transformation. What is the matrix of a linear transformation? Therefore, the matrix of f dash of x is nothing but though that is d1 f1 of x J is 1, D1, F2 of x, comma, etc., etc., B1, Fm of x. What is f dash of x at E2? J equal to 2, therefore B2 F1 of x, etc., etc., B2 Fm of x. So we can complete this matrix that dn f1 of x, etc., etc., dn fm of x. So it is an m by n matrix. Friends, I am interested only if m equal to n. Friends, if m equal to n, if m equal to n, then matrix f dash of x is a square matrix, a square matrix. So I can talk of determinant. Therefore, in this case, determinant of f dash of x is called Jacobian of f at x. You all know determinant of f dash of x not equal to 0 if and only if f dash of x is invertible. So there is a very interesting concepts that are available in any books. Even a student of first BSc or second BSc, when he is studying that multivariate, sorry, double and triple integral, they are they are having this idea Jacobian for changing variables. So this play a vital role. Friends, now listen here. F, and suppose f is a function from R2 to R2 defined by f of x comma y equal to e power x times cos y comma sin y. Friends, if you consider R2 as a complex plane, then what is this map? F of z equal to e power z. This map is e power z. So it is analytic that we can say more about this. And friends, this map, what do you say about what about this can be written as f1 of x comma y comma f2 of x comma y by f1 of x comma y equal to e power x cos y, and f2 of x comma y equal to e power x sin y. I am talking about the Jacobian of f at x comma y. This is equal to the determinant of what is dou f1 by dou x, that is e power x cos y, dou f2. So partially this is e power x sin y. So now this dou f1 by dou y. What is this? Dou y. So this is minus e power x sin y. This is e power x cos y. So what is this? E power 2x, never 0. Therefore, this function, its derivative is invertible, not any. So this shows that this gives f dash of x comma y for every x comma y in R2 is invertible. But one thing, friends, globally this function is not invertible. For example, what is f of 0 comma 0? F of 0 comma 0 is e power 0 1, cos 0 is 1, 1 comma 0. What is f of 0 comma 2 pi? E power 0 is 1, this is 1, cos 2 pi is 1, and the sin 2 pi is 0. So 1 comma 0. That, friends, This is a right example. Though its derivative at any point is, sorry, I made a mistake. This is a pair where x comma y belongs to R. Okay, sorry. Sometimes I write loosely. Sorry, friends.
ஹலோ
So f of 0 comma 0 is 1 comma
தம்பி
0 and
ஒன்றும்
f of
இல்லைப்பா
0 comma
எனக்கு
2y is
நைட் நீ அனுப்பிச்சிருந்தீங்க நான் பார்த்தேன் அதில்
1 1
ஃபோட்டோஸ்
comma
வந்து
0.
நிறைய
Therefore,
மாறி இருக்கு.
f is
அது எதில் மாறி இருக்குன்னா
f is even,
கான்ஃபரன்ஸ் காலுக்கு ஒரு ஃபோட்டோ வச்சுருக்குல்ல,
not n.
அது விஓசி காலேஜில் உள்ள
It is
கான்ஃபரன்ஸ்
not
கால் கிடையாது, அது
invertible.
பிஎட் உள்ளது.
Friends,
இல்லைடா
now
நீ
I want to say something about
சரியா இப்போ ஒன்றும் பிரச்சனை இல்லை.
that
இது இது
script
இப்போ
C1.
எனக்கு 11:30க்கு ஒரு மீட்டிங் முடியும். அந்த மீட்டிங் முடிஞ்சோடனே எந்தெந்த ஃபோட்டோ மாற்றணும், அதே மாதிரி எம்ஓயூஸ் எல்லாத்துலேயுமே எம்ஓயூக்கு பக்கத்தில்
So,
அப்பாஸ்ட்ரோஃபி எஸ் போட்டிருக்கேன்.
what?
சரியா, பேராகிராஃபில் எழுதும்போது நிறைய எம்ஓயூ பின்னாடி வருதுங்கிறதுனால எம்ஓயூ
Friends,
பக்கத்தில் அப்பாஸ்ட்ரோஃபி எஸ்
please
போட்டிருப்பாங்க. அது
wait
ஆக்சுவலாக
for
அப்படி
some time.
போடக்கூடாது.
I come and check.
தனித்தனியாக போடும்போது அப்படி போடக்கூடாது. இல்லை அதான் சொல்கிறேன், நான் உனக்கு பேராகிராஃபாக அனுப்பிச்சிருந்தேன். எம்ஓயூஸ் வித் பாரதாசன் இன்ஸ்டியூட் ஆஃப் கேரியர் டெவலப்மெண்ட் வித் பிட் ஸ்டெப் ஃபார் ஸ்போக்கன் இங்கிலீஷ் கோர்சஸ் அப்படின்னு அனுப்பிச்சிருந்தாங்க. அதனால நீ அந்த எம்ஓயூ பக்கத்தில் அப்பாஸ்ட்ரோஃபி எஸ்ஸோடையே சேர்த்து போட்டிருக்க. முதல் 2 இருக்குது, அதுக்கப்புறம் கரெக்டாக போட்டிருக்க. எம்ஓயூ வித் எம்ஓயூ பக்கத்தில்
Sorry,
அப்பாஸ்ட்ரோஃபி
friends.
எஸ் வராது.
I'm sorry.
சரியா, நீ
Somebody
ஒன்றும் கவலைப்படாத.
responded. I
இப்போ
don't
நான் இப்போ
feel
11:45க்கு அப்புறம் உனக்கு எல்லா கரெக்ஷன்ஸையும் ஒரே இதில் போட்டு அனுப்புகிறேன்.
Friends,
அதுக்கப்புறம் நீ அதை
I'm going
மாற்றி
to
எனக்கு
introduce
அது
the
வரைக்கும்
next
பொறுமை.
one that is very
சரியா,
interesting.
அதே மாதிரி அலுமினியில்
Script C1.
பிரகஸ்பதி முன்னாடி இருந்து அதே ஆள் வச்சுருக்கல, அதுக்கு பதிலாக வேற ஒரு ஆள் நான் சர்டிஃபிகேட் வாங்கியிருக்கேன்.
What is script
அவரை
C1?
அனுப்புகிறேன். அவர் இதை
Continuously
ஓகேவா.
deposition.
உன்னோட இன்னொரு வீடியோ ஷேர் பார்த்துட்டு என்ன சொன்னாங்கன்னா, நம்ம அட்மிஷன்
What
கொடுக்க
is
இன்னும் சரி
continuously
அப்ளிகேஷன்
deposition?
ஃபார்ம் லிங்க் இன்னும் இதாகலை. அதாவது கவர்மெண்ட்
Derivative
சொன்னதுக்கப்புறம் தான்
is
நம்ம அப்ளிகேஷன் கொடுக்க ஆரம்பிப்போம். அப்படி அப்ளிகேஷன் கொடுக்கறதுக்கு ஒரு நாளைக்கு முன்னாடியிலேருந்து அந்த வீடியோவை நம்ம
and
சர்க்குலேட் பண்ணுவோம்னு சொல்லியிருக்கோம்.
derivative is continuous.
ஏன்னா அதில் இந்த வெப்சைட்டுக்கு போகணும், விஓ சிதம்பரம் காலேஜ் கிளிக் பண்ணணும் அப்படின்லாம் வருது இல்லை. ஸோ அப்ளை பண்ணுறவங்களுக்கு அது
You
யூஸ்ஃபுல்லாக இருக்கும். நம்ம
may
இப்படியே
come across
போட்டால் அதை
that
சர்க்குலேட் பண்ணிட்டு அப்படியே விட்டுருவாங்க.
any analytic function is
நம்ம அட்மிஷன் போடும்போது அதுக்கு ஒரு இந்த லிங்க் போடுவாங்கல்ல, அட்மிஷன் லிங்க், அந்த லிங்கோடு சேர்த்து இந்த வீடியோவை
Friends,
நான்
there is
ஃபார்வர்ட்
one
பண்ணி விடுவோம்.
characterization.
சரியா,
Let
ஓகே.
EB and open subset of n and F from E to R. Then it belongs to script C1 if and only if all Bj Fi edges and are continuous. So this is very, very interesting concept. And friends, this result is somewhat easy. So my aim is not to prove this, but to go for some more things. Friends, I will take, actually now the time is 10:54. I have 30 minutes, so at least I can mention something about that. What is that? Inverse function theorem. So I am moving towards that. Friends, now listen here. One thing I can say that what is contraction method? Friends, it was introduced in 1922 by Stephen Bennett in his thesis, a map f from x to dx to y to dy. We say f is a contraction. If and only direct this, a constant k belongs to open close to 0 open 1 such that dy of f of x comma f of y is always less than or equal to k times dx of x comma y. Friends, this map is obviously uniformly continuous. This map is obviously uniformly continuous. Therefore, mm, this maps causes sequence to causes sequence. If you come across variants of Banner contraction principle, uh, some others assume the domain as the complete metric space, some others assume the codomain is the complete metric space. Domain may not be. The codomain is complete, then there exists a unique fixed point. So I am not interested in doing this. And let f from x to x. F is a self map. X is a metric space. A point x belongs to x is said to be a fixed point of f if f of x equal to x. So if x satisfies this equation, f of x equal to x. This is the, so x is the invariant point under the map here. If it is so, then x is called a fixed point. So fixed points play a major role after the Banner contraction principle, especially for application of mathematics. And I am not going to talk more about on this, but anyhow, my goal is to at least to mention what is the inverse function here. Okay, friends. Now listen here. And what about this Banner contraction principle? Let x comma d be a complete metric space. You all know what is the definition of a complete metric space. What is that? A metric space in which every causal sequence is convergent to a point of x space is called a complete metric space. Let f from x to x be a contraction. Then there exists unique x belongs to x such that f of x equal to x. Not only that, friends, if xn plus 1 is defined by f of x, f of xn with the initial point x naught in x, then the sequence then the sequence xn is a causal sequence that converges to x, fixed point of ascent intensity. Friends, the proof is very, very interesting. One can easily prove that d of xn comma xn plus 1 is always less than or equal to k power n into d of x naught comma x1, where k is the contractive constant. And this definition says that xn is a causal sequence. Xn is causal. This gives there exists x belongs to x because x is complete such that xn converges to x. And friends, since f is continuous, f of xn converges to f of x as n tends to infinity. Therefore, f of x equal to limit tends to infinity f of xn. But what is f of xn? Limit n tends to infinity xn plus 1, a subsequence of xn, original sequence converges to x. Therefore, its subsequence also converges to x. Therefore, f of x equal to x. X is the fixed point of the limit of the iterative sequence. Okay, friends. Recall what we have seen so far. One thing, if A belongs to L of Rn comma Rn, then A is invertible. A is bounded, and hence A is uniformly continuous. Second, if A is invertible and B is linear on Rn, and if norm B minus A times norm A inverse is less than 1, then B is invertible. Third one is, if f is differentiable, then f from E subset of Rn to Rn is differentiable, then f of x at Ej equal to summation dj fi of x in the R. Okay, friends. And the fourth one is Banach contraction also. Okay. So with this, I am going to introduce inverse function theorem. What is inverse function theorem? Let E be an open subset of Rn. Let f from A to Rn be a zero mapping, continuously differentiable. Let A in V such that f dash of A is invertible. Let B equal to f of V. Then I have two conclusions. Then there exist two open sets, U and V in Rn, such that A in U, B in V, and f from U to V is bijective. Second one, if G equal to F inverse from B to W, sorry, B to A, then G belongs to script sigma. Friends, I want to say more about this. What is the first conclusion? There exist two open sets, U and V in Rn such that A in U, B and B in V, and F from U to V is bijective. Friends, what is f of U? Equal to V. So f is a open mapping. F is a open mapping. Friends, recall what is the definition of homeomorphism. Let f from x to x and y are two spaces, and f from x to y be a function. We say f is a homeomorphism if and only if first one f is bijective, and second one both f and f inverse are continuous. So a bijective bicontinuous map is called a homeomorphism. Friends, two characterizations are obtained. A bijective map which sends open sets to open sets is a homeomorphism. Bijective map, F is a homeomorphism if and only if it is bijective and it sends open sets to open sets. Similarly, F is a homeomorphism if and only if it is bijective and it sends closed sets to closed sets. You know topological properties and homeomorphism. So, homeomorphism play a vital role. Friends, this first result shows that if f dash of A is invertible, in the neighborhood of A, the equation y equal to f of x is solvable. Why? Y equal to f of x means, so x belongs to u such that y equal to f of x implies x equal to f inverse of y. Because f is bijective, if and only if it is invertible, therefore a system of n equations with n unknowns is solvable. Friends, how strong the result is? You just imagine. For a system of linear equations with linear m equations with n unknowns, to have a non-trivial solution, we need conditions. M must be less than A here. So f, the equation y equal to f of x is solvable in the neighborhood of A if and only if f dash of A is invertible. How strong the result is. Friends, in 1957, that was the year of my birthday, in American Mathematical Monthly, this inverse function theorem using fixed point theory appeared, and the proof in the Walter Rudin is derived from that paper. Walter Rudin used that paper to write this proof. So this is very, very strong. But one thing, this may mislead you. F is an open map. You may suddenly come to the conclusion that it is a homeomorphism. Friends, I can give you an example that this homeomorphism is local but not global. What is the example? Already I told you about that example. F from R2 to R2 defined by f of x comma y equal to e power x cos y comma sin y is differentiable, sorry, its derivative at any point is invertible, but this map is not a homeomorphism, locally homeomorphism. So even it is not 1-to-1. So this example shows that this inverse function theorem is local but not global. Okay. Friends, Professor Jackson, how
Sir,
long should I go? How long should I go?
sir, it's your wish, sir. Time is now 11:10. 20 more minutes.
Shall I go?
Yes, Professor. 20 minutes. So till 11:30 we can. Shall we proceed?
Okay. Oh, I have enough materials to go up to 1 o'clock. No
Yes,
problem.
Professor. Yes,
Okay.
Professor. I know. I know.
No
But
problem. No problem.
normally the lectures will from
Well,
10 to
okay.
11:30. That's why, Professor.
Okay. We will wind up before 11:30.
Sure,
So,
Professor.
friends,
Thank you, Professor.
thank you. Okay, friends, I will give you some hints about this mm, proof of this inverse function then. Proof is very, very interesting, not only interesting, and actually we can enjoy a lot in seeing this proof. Actually, I write A equal to f dash of u. This gives A is invertible. This gives A, friends, one thing, a linear operator which is invertible, then its inverse is also linear. This gives A inverse belongs to L of Rn. So this is obvious. A linear if a operator is linear and if it is invertible, then inverse is also linear. Okay. This gives A inverse is bounded. Therefore, I can find a lambda greater than 0 such that 2 lambda times norm A inverse equal to 1. So, I can find a lambda suitably so that 2 lambda times norm A inverse equal to 1. You may surprise that why you choose lambda. Actually, the next two lines shows that the author chose lambda in such a way that 2 lambda times norm A inverse equal to 1 with a very good ambition. I will tell you why. Now listen here. Since f dash is continuous, A belongs to E, given lambda greater than 0, there exists delta greater than 0 such that x belongs to B of A comma delta implies norm f dash of x minus f dash of A is less than lambda. Friends, I write this as what is open ball about A of radius delta as U. I write let U equal to B of A comma delta. This gives U is open convex set containing A. Any open ball is a convex set and it's an open set. Therefore, U is an open ball about A of radius. So, thus for every x belongs to B of U, now f dash of x minus f dash of A. What is f dash of A? I write it as A. So, f dash of x minus A is less than lambda. Friends, now listen here. What is this gives? For every x belongs to U, norm f dash of x minus A times norm A inverse. This is less than lambda, but this is equal to 1 by 2 lambda. So, this is equal to 1 by 2, which is less than 1. Friends, there is one result. What is the result? That second result. If B is linear and A is linear, which is invertible such that norm B minus A times norm A inverse is less than, then B is invertible. So, using this gives, for every x belongs to U, f dash of x is invertible. How the result is? That is why the author choose lambda in such a way that 2 lambda times norm A inverse is less than. Okay. Now listen here. For each y belongs to Rn, I define a function. Define phi by phi of x comma phi of x equal to x plus A inverse of y minus f of x. Friends, x belongs to Rn, A inverse belongs to L of Rn, y minus f of x belongs to Rn. Therefore, phi is a map from Rn to Rn. In particular, phi is a map from E to Rn. Okay. Friends, what is pi dash of x? Now listen here, pi of x equal to x if and only if A inverse of y minus f of x equal to 0. That is if and only if y minus f of x equal to A of 0, A linear, it sends 0 element to 0. That is if and only if y equal to f of x. Friends, one thing I want to say about the Banner contraction principle. So what is recall the Banner contraction principle? A contraction map on arithmetic space has a unique fixed point. If you, one thing I want to say that both conditions are necessary. That contraction is necessary and completeness is necessary. You cannot relax these two conditions. For example, in Rn, if you define f of x equal to x plus a, then f is not a contraction map, and the translation is not a, it doesn't have a fixed point. So similarly, any contraction map defined on open interval a comma b to open interval a comma b by f of x equal to x by 2, definitely it is a contraction map. It doesn't have a fixed point. So both the conditions are necessary. Therefore, what is the conclusion is any contraction map on a metric space has at most one fixed point. So, friends, what is pi of x? Pi of x equal to x if and only if y equal to f of x. If pi is a contraction map, then there exists at the most one x belongs to E such that pi of x equal to x. If and only if there exists one x belongs to the domain such that y equal to f of x means that function f is a one-to-one map. So, to prove f is 1, 1, it's enough to prove. Pi is a contraction. Okay. You all know what is, I rewrite, what is pi of x? I rewrite pi of x equal to x identity map I of x plus A inverse of y minus f of x. So now I differentiate. So what is pi dash of x? Pi dash of x equal to I is linear, therefore its derivative is I itself, plus A inverse is linear, therefore A inverse of y is constant, f dash of x. So this is equal to I minus A inverse of f dash of x. If I take A inverse outside, this is A minus f dash of x. Friends, therefore, norm pi dash of x equal to norm of A inverse of A minus f dash of x. Which is less than or equal to norm A inverse times norm f dash of x minus a. Friends, if x belongs to u, this is less than lambda. This is 1 by 2 lambda. Therefore, this is less than 1 by 2 lambda times lambda, that is equal to f by 2. Friends, there is one theorem that shows that a map that satisfies this condition is a contraction map. This gives by theorem for every x1 comma x2 in U, norm of pi of x1 minus pi of x2 is less than or equal to 1 by 2 times norm x1 minus x2. This gives pi is a contraction. Therefore, there exists at the most one x belongs to u such that pi of x equal to x, if and only there exists at most one x belongs to u such that y equal to f of x. This gives f from u to Rn is 1. Friends, if I write v equal to f of u, then f from u to v is by v. That proving v is trivial. I leave it an exercise to the readers or the audience. And the first part is obvious. Friends, how interesting the theory is. In functional Cs, you are talking about the bounded linear functions. Here, boundedness is not necessary because we are sitting in a finite dimensional space. Therefore, any linear functionals defined on a finite dimensional space is automatically. So, there are many derivatives available in functions. Frache and I have forgotten some names. Frache derivative and I don't know. So, if one wants to do research in functional space, he should go through the 9th chapter of Rule very well. So, how the linear functionals defined on finite dimensional space behaves, then you can extend this result to infinite dimensional space by assuming only one condition, boundary. That's all. Friends, this is a nice occasion, and once again I thank my friends, professors in the Department of Mathematics of VOC College. They provided me a platform to meet all of you. So I once again thank them. Now I invite audience to ask doubts.
So, dear participants, now it's your time. If you have any doubts, you can raise your questions now. You can unmute yourself and ask your questions. Otherwise, you can put your questions in the chat box. It will be represented. Those persons who are watching this through YouTube, you can put your questions in the YouTube chat box, a live chat. It will be represented here. Please.
Professor, shall I conclude my talk?
Sure, Professor.
Thank you, friends. Thank you, one and all. Thank you, friends. I conclude with this. Thank you.
Thank you so much, Professors. I think since Professor's talk is crystal clear, so that and also it is with some clear ideas, but definitely professors will know how to teach analysis. Definitely, professors, it's a reference. It's a reference talk for us, for budding
Thank you.
teachers. So thank you, dear professor.
Thank you.
I request Professor Safina Devi to propose the vote of thanks.
Good morning, everyone. It is my privilege to propose the vote of thanks for today's session of the Faculty Development Program organized by UG and Research Department of Mathematics, VO Chidambaram College. Firstly, I express my heartfelt gratitude to our Honorary Secretary, Sri APCV Chokalingam, for being the pillar of support for every event happening in our college. I express my sincere thanks to our principal, Dr. C. Veerababu, for his motivation and support for organizing this faculty development program. On behalf of everyone, I express my deepest gratitude to our resource person, Dr. Marudai. Sorry, sir, Dr. M. Marudai, Honorary Professor of Mathematics, Bharatidasan University. Thank you, sir, for taking out time from your busy schedule to share your expertise and thoughts on this topic of multivariate calculus. The session was lively and it was like we were in the classroom, not an online meeting. Thank you, sir. And
Thank you.
it was not just informative and insightful, but also it was an educated session as to how to systematically arrive at results in not only multivariate calculus, but in any subject of mathematics. Thank you, sir. I once again say a very big thank you to you. I now express my profound gratitude to our beloved head of the department, Dr. A. Nagarajan, coordinator of the faculty development program, for providing us this opportunity to participate and share with the expertise of our eminent resource person. Thank you, sir. I extend my sincere thanks to the organizing secretary, Dr. S. Jackson, and all other faculty members of our department, and every staff in our college, teaching and non-teaching, who have put in their efforts for the successful um, ongoing of this program. I express my deepest sense of appreciation and gratitude to our participants gathered here. We hope today's seminar was informative and useful to you. Last but not least, I would express my gratitude to the Almighty, with whose blessings and grace we are able to make this event what it is. Thank you, one and all. Over to you, Jackson, sir.
Dear participants, your feedback link is there in the chat box. Please fill it. It will be open for next 15 minutes. So fill it as early as possible. So yesterday some of you couldn't fill the feedback form.
Jackson, sir.
Professor, shall I wind up my?
Yes, yes, professor.
Shall I close?
Thank you,
Mother sir,
professor.
Mother sir, thank you very much.
தேங்க்யூப்பா தேங்க்யூப்பா
தேங்க்யூ சார்,
எப்படி
தேங்க்யூ.
நம்ம
சூப்பரா
பேசிக்கிறோம்.
இருந்தது சார், நல்லா இருந்தது. சிஸ்டமேட்டிக்கா டீச்சிங் நம்ம கிளாஸ்ல கேட்ட மாதிரி நல்லா நீட்டா இருந்தது. ஐ திங்க் nobody has asked any question. It is very clear. நல்லா சிஸ்டமேட்டிக்கா இருந்தது. ஃப்ரம் த பிகினிங் இருந்தது இல்ல, ஃப்ரம் த ஸ்கிராச் ஆரம்பிச்சதுனால it will be very easy to follow.
தேங்க்யூப்பா தேங்க்யூ ஸோ மச்.
Thank you.
பை.
Jackson sir,
Yes, ma'am.
Yes, ma'am.
if you may அந்த ரெக்கார்டிங் ஸ்டாப் பண்ணதுக்கு அப்புறம் கூட ஒரு 10 மினிட்ஸ் கூகுள் மீட் ஓபன் பண்ணி வச்சிருக்க முடியுமா? ஏன்னா லிங்க் இருந்தா ஃபீட்பேக் பார்த்துக்குவாங்க, ஃபீட்பேக் லிங்க்.
Sure, ma'am.
Sure,
Sure, ma'am.
ma'am. Sure, ma'am.
தேங்க்யூ தேங்க்யூ.
Nagarajan sir, welcome to our department Google Meet.